Welcome to the channel. Today we're looking at the mechanics of deep time. Before the Earth existed, there was no sky to gaze upon, no space to hold stars, and no time to measure. It was a dense, silent void. Then a sudden ignition occurred. Space began to violently expand, and from that initial outward pressure, the universe forged its simplest, lightest ingredients, hydrogen and helium. Deep within this expanding darkness, the first massive stars ignited. They functioned as enormous cosmic furnaces, crushing light elements together under extreme gravity to forge heavier ones, like carbon, oxygen, and iron. When those massive stars eventually died, they detonated, scattering their internal materials across the void as thick clouds of dust. Those wandering clouds of scattered ash hold the raw physical matter of our reality. The iron in the planetary core, the oxygen in the water, and the carbon inside every cell are all recycled remnants forged in the fires of dead stars. This diagram shows a flat protoplanetary disk of dust and rocky fragments. When a localized shockwave, likely from a nearby stellar explosion, disturbed a cloud of stellar ash, the center collapsed and ignited into our young sun. Around it, gravity pulled the remaining spinning debris together, aggregating into massive rocky bodies. As we look closer at this isolated mass, you can see how the intense heat from constant impacts caused a process called differentiation. Differentiation is the physical separation of materials inside a planetary body based on their density. Heavy metallic elements, like iron and nickel, sank inward to form a dense core, leaving lighter silicate rocks on the outside to form the mantle and crust. As the young Earth cooled, a Mars-sized planet named Theia entered its orbital path. It struck the Earth at an oblique angle. The sheer kinetic force of the impact vaporized the outer crust and violently ejected a massive ring of glowing debris directly into the dark void. Gravity rapidly captured that ejected material. Within a matter of weeks or months, the dense ring of fragments compacted together into a single large sphere, forming our moon. That newly formed moon acted as a vast gravitational metronome. Its constant pulls stabilized the Earth's chaotic axial tilt, locking the planet into a steady rotation. That mechanical stability established the regular, predictable seasons that biology would eventually need to survive. Earth's surface was initially a boiling ocean of magma beneath a heavy, toxic atmosphere. But as the planet slowly radiated its heat into space, temperatures dropped enough for the atmospheric water vapor to condense. This triggered a prolonged phase of extreme weather. Continuous heavy rain that fell onto incandescent rocks, evaporated instantly, and rained down again for millions of years. That relentless hydrological cycle rapidly drew heat away from the crust. Once the surface cooled sufficiently, the evaporating water remained liquid on the ground, gathering dissolved metals and minerals as it pooled to form the first dense oceans. The moon was much closer to the Earth then, looming massive in the sky. Its intense gravitational pull dragged enormous tides back and forth twice a day, violently churning the chemical ingredients pooled along the coastlines and mixing them with the mineral-rich boiling water erupting from deep-sea hydrothermal vents. Those cyclical shifts, constantly moving between wet and dry, hot and cold, forced scattered molecules into tight proximity. Under these precise conditions, molecules began snapping together to form fragile chemical films. They enclosed tiny droplets of water, establishing the first definitive boundary between an inside environment and the outside ocean. There was no single magical spark of life. Across billions of tidal pools, over epochs of deep time, the environment relentlessly tested trillions of these drops. Only the rarest chemical sequences survived, the ones that accidentally developed a method to trap external energy and imperfectly copy their own structures. At first, these fragile biological systems survived solely by tapping into local geothermal heat. But a critical turning point arrived when primitive, single-celled structures developed a mechanism to capture and utilize the raw radiation from the sun. They evolved to use photosynthesis. Photosynthesis is the process by which organisms convert water, carbon dioxide, and solar radiation into physical cellular growth and usable chemical energy. This new biological engine produced a highly reactive waste product, oxygen. As these early cells released free oxygen into the oceans, it violently oxidized the massive reserves of dissolved iron. This reaction created heavy, deep red rust particulates that precipitated out of the water, raining down continuously to coat the dark, rocky seafloor. Once the oceans and seafloor rocks could absorb no more oxidized iron, the relentless accumulation of oxygen bubbled up and flooded the atmosphere. High above the surface, it reacted to form a thick ozone layer, casting a protective shield that blocked the sun's most lethal ultraviolet radiation. Harnessing solar light gave these organisms a massive surplus of energy, providing the exact caloric fuel needed to build complex biological structures. By simply existing and multiplying, they re-engineered the planet, shifting it from a hostile, toxic chemical bath into a breathable, heavily shielded sanctuary. In the open sea, certain large cells began to physically engulf smaller, energy-producing ones. Instead of digesting them, they formed cooperative packs. These merged cells operated as stable biological factories, utilizing their combined energy to divide labor into highly specialized roles, like transportation and structural protection. With these larger, complex structures came the need for massive amounts of fuel. Certain organisms began actively consuming other living things. The advent of predation introduced a brutal, direct method of acquiring concentrated biological energy. Predators had to locate and catch, prey had to resist or escape. This relentless pressure ignited a severe evolutionary arms race. Organisms rapidly developed articulated muscles for sudden movement, thick external shells for armor, and refined sensory organs to detect threats in the water. This diagram shows the specific mechanical evolution of the eye. It began simply as a flat layer of light-sensitive spots on the skin. Over countless generations of selective pressure, that layer curved inward to form a recessed cup, allowing the organism to determine the specific direction of incoming light. Over time, the aperture narrows entirely, creating a natural internal lens capable of projecting sharp, actionable images. The rhythmic, violent cycle between hunter and prey acted as a biological forge. It aggressively accelerated the intelligence, anatomical variety, and spatial awareness of marine life across the globe. As shifting continents created shallow, temporary tidal zones, marine life faced a new frontier. Fish living in coastal pools pushed outward into the open air for brief moments, exploiting the much higher concentration of atmospheric oxygen. Leaving the buoyancy of water required severe anatomical adaptations to combat the crushing force of gravity. Coastal fish evolved fins that hardened into weight-bearing limbs, capable of digging forcefully into wet mud, while internal air sacs repurposed into primitive lungs. The final physical hurdle was reproduction. The earliest landwalkers still had to return to water to lay their eggs. True terrestrial independence was only achieved when organisms bypassed the water entirely by developing a protective shelled egg that encased the embryo in its own portable liquid environment. Organisms did not simply leap out of the ocean. The terrestrial invasion was a grueling march of millions of microscopic physical adaptations, gradually transforming a lethal atmospheric barrier into a habitable environment. The evidence of this deep timeline is physically readable today. We can track the precise shifts in planetary conditions through the imprints left in ancient crystal structures, massive bands of oxidized marine rock, and the fossilized domes built by early biological communities. From these geologic records, we can identify the three universal requirements for biological complexity: a physical boundary that protects the organism, a viable method to capture energy, and a self-replicating chemical system capable of retaining useful structural errors. However, empirical observation reaches a strict limit. We can trace the chemical steps of life and map the orbital mechanics of our solar system, but the exact nature of the initial energy that moves space and matter, and why these specific physical laws govern existence, remains unknown. The hard data maps a clear sequence. A cold cloud of ash structurally organized itself into a breathing, stable world. Yet the underlying catalyst driving that sequence is still a profound mystery. We map the mechanics of Earth to the edge of the evidence, and right there at the boundary, the search for what comes next continues.